Let's talk about the section C and section D of our data science paper. I will cover all the topics which are used in these sections. So let's start. Data preprocessing for feedback analysis. Effective feedback analysis begin with robust data preprocessing. This section explores critical steps to ensure data quality, handle missing values, smooth rating, and integrate diverse datasets for comprehensive insights into the students and faculty performance. So I have distributed everything within sections and chapters. So I will talk with every chapter one by one. So here it is, chapter 1. Ensuring data quality, accuracy, completeness, and consistency. Accuracy issues. Data may be inaccurate due to errors in entry or perception, such as a student McKinley selection wrong, rating option, or faculty self-rating themselves too high. This can lead to misleading conclusions. Completeness challenges. Missing survey response are a common problem if a significant number of students skip certain question or entire survey. The data sets become incomplete, making it difficult to draw reliable conclusion about specific courses or instruction. Consistency problem. Contradictory ratings are varied scaled across different feedback from forms can lead to inconsistencies. For example, a student might rate an instructor highly on one metric but poorly on another rating metric without clear justification. Other dimensions of data quality. Timeliness. Data must be correct and available when needed. Outdated feedback might not reflect current performance or student sentiment, leading to irrelevant or inefficient interventions. Relevance. Data should be pertinent, pertinent to the analytical goals. Collecting data that doesn't directly contribute to understanding a student's faculty feedback can clutter the data set and obfuscate values inside. So let's come to chapter 2, strategies for handling missing student feedback values. Ignoring tuples. Simplest approach, removing records with missing values. However, this can lead to significant data loss, especially if missingness is widespread, potentially biasing the analysis. Manual filling. Experts review and manually input missing data. This is highly accurate but labor intense and impractical for large data sets. Constant value imputation. Fill missing values with constant like the mean, median, or mode of the attributes. This maintains dataset size but can reduce variance and distort statistical relationships. Class specific imputation. Apply constant value imputation within specific classes, e.g., mean rating for particular courses. This improves accuracy by considering context. Most probable value. Use the statistical models, e.g., regression decision tree, to predict missing values based on other attributes. This is more sophisticated and can yield more accurate imputation. Chapter 3, Smoothing Data and Detecting Outliers. BIN means smoothing. To smooth rating using bin means with bin depth 3. We first sort the data, then divide into bias of size 3 and replace each value with the mean of its bin. I have given the example, you can check it out. Detecting outliers. Outliers such as abnormally high or low satisfaction scores can be detected using various methods. First is box plots, identifying values outside the wrinkles, typically 1.5 times the interquartile range IQR from the first and third quartile. Z index, flag values with Z scores exceeding the certain threshold, e.g., IZI greater than 3, indicating they are many standard deviation away from mean. Other data smoothing methods. First, the bin medians. Replace all values in the bin with the median value of that bin. This is less sensitive or to extreme values that bin means. Second, bin boundaries. Replace values in a bin with the closest boundary value, minimum or maximum of that bin. Third, regression. Fit data to the a regression function, smoothing by approximating the data with a mathematical model. Number four, clustering. Group similar data points into clusters and then smooth the data within each cluster by replacing values with cluster centroids. Data integration for ME MTech analysis. Schema integration, combining metadata from multiple sources, identifying similar attributes, and resolving semantic heterogeneities. The end includes naming conflicts, e.g., student ID versus student ID, and structure conflicts, handling redundant data, detecting and eliminating duplicate entries that arise from multiple surveys or data collection points. Redundancy can influence counts and skew statistical analysis, requiring careful merging and deletions, resolving conflicts, addressing conflict values for the same attribute from different sources, e.g., varying student scores for the same assignment. This often involves stabilizing precedence rules, averaging values, and consulting a trusted source. Chapter 5, Normalization Method for Data. Min-max normalization. Scale values to a specific range 0 to 1. Formula fit min by max to min. Useful for algorithms sensitive to input scale. Z-score normalization. Transformation values to have a mean of 0 and a standard deviation of 1. Z score, Z score, which is mad. Use mean absolute deviation instead of standard deviation for robustness against outliers. Decimal scaling normalizes by moving the decimal point of values, typically to ensure the absolute maximum value is less than 1. Example is there. Normalizing faculty workload values. So here it is the table original values is given. When normalizing the feedback of rating of 35, mm, min max 0 to 1 range, and Z score within this value, and decimal scaling is the most appropriate as it handles outliers and maintains relationship. Our last chapter 6, attribute selections and techniques for feedback analysis, forward, backward, and hybrid. Attribute selection is crucial for reducing dimensionality and improving model performance in feedback analysis. Each method offers a different trade-off between computational cost and accuracy in finding the optimal subset of future. Thank you.